Hello, so welcome to another video on how to solve models in Python. In this video, we are going to look at similar problem that we solved earlier, but we want to try out different kinetic models. So we want to see how we can uh, evaluate the performance of the reactor by using different kinetic models, like the elementary kinetic model, power law, so Langmuir, Ishen-Wood, and so on. So these are the model equations, and then these are the various models. So model one, which is the elementary one, the power law, the Langmuir Asian wood, and so on. Okay, so how do we solve this in Python? We first import the packages, you define the parameters, these are the parameters, and then you write the functions. So these are the kinetic models. So that we have the kinetic constant rather. These are the kinetic constant, and then this is the function for the model. So within the function, again, the function will call or will when you call this function, it's going to take these variables. So and pass them as arguments. But one additional parameter that you need to pass is this model underscore ID. So when you solve underscore IVP requires you to pass two arguments. So that means we will need to use args to pass the other parameter here. So xt, yp, and you extract them from the variable, well, from the vector that we have. This will be a metric basically. And then you calculate the concentrations. These are the rates. So you run these function. We call these functions in order to calculate the K value and the Kc values. Now here is the difference compared to what we did before. So we need to use the appropriate kinetic rates, the appropriate rate model, depending on which one we want to use. So if the model ID is 1, then use the elementary model. For example, if model ID is 2, use the power law model, and so on. And that's what we're trying to do. If, elif, elif, so if it is not 1, then if it is 2, use this model. If it is 3, use this model. If it is 4, use that model. And then otherwise, if it is none of those, if you pass anything outside of these numbers, then you raise a value error. Okay. Now, what are the ODEs? These are the ODEs that we have, similar to what we had before, and then we'll return the derivatives, which are the left-hand side of the differential equation. So now we need to simulate the model. We need to run the model. So still define how long we want to run from 0 to 20. And then again, WEval, we want to evaluate at 400 points between 0 and 20. And then we create a dictionary to store the result. Okay, so trying to store the result here. So we loop through the model. So for model in range, because we need to do from 1 to 5, so it doesn't include this the last number in the range. So we solve each time. We pass these arguments. These args will pass the value of the model ID as an additional argument. So remember, that function needs to take additional ID, which is the model ID, and that is what we are going to pass as an argument. Okay, and that model ID is this model. Is the parameter model there. So this model parameter will be changing from 1 to 5, and each time it's going to assign the current value of model, in order to assign the correct kinetic model. So this stays the same, similar to what we did before, except that we are changing the value of model in order to assign the correct kinetic information, or the right kinetics. So we store the result each time that we run. So result, and then the value, the result for the particular model, for model 1, is going to be solved. And we store that. When it runs again, when it is 2, it saves the value it saves the result there. When it is 3, it saves the result there. When it is 4, and so on. And then we can use the key to access the value of the result that is stored in Sol later on. Okay, so these are the labels that we have for 1, 2, 3, 4, 5. So they correspond to each of these models, and then we plot. So we call the plot the figure function, and then the subplot. So what we're doing here is that we are looping through the solution. Remember, there are 5 different solutions stored within Sol. So, but we need to access the one where we are looking for. So M, we are doing for M comma Sol in results. Remember, results is a dictionary. So when you do result dot items, so you can access the key and the value. So when M is 1, so when it passes 1 into the as a label, you can access the result that is stored, the Y value that is stored within Sol. So, and then you plot it. So when M becomes 2, then you access the result that is stored in Y um, for the second kinetic model, and so on. And that's what we're trying to do here. So we're trying to grab the results for the different kinetic model when we assign the different M values, which correspond to the value. Remember, that's what we're trying to do here. So the M is what is representing 1, 2, 3, 4, 5 here. And then we plot the result. So after that, then we extract the solution. So here we are just recalculating the values of the concentration by us. When we extract the result for the Sol, then based on that, if we just plotting, for example, one of the model 3, separately, and then we plot that. Then when we run it, so we should generate the values. Yeah. So here, what I did before is that if I want to plot model 3 separately, we just plot the concentration of reactant and product for a particular model, which is model 3. That is what this panel is showing. To the other panel, they're showing the conversion value for the various model. So for the power law, so it shows that the power law has the highest conversion. You can see that, and then the temperature profile for each model. So you can see that the other model, they show similar behavior, except the power law. Okay. For the pressure drop, the power law also has slower pressure drop, and that's it. That's how you can try different models, uh, try different kinetic model when you have a packed pegged reactor. It doesn't matter, the kind of model that you have, but the key thing here is how do you try those different models? So, which is this part. So where you are assigning the model ID in order to select the right kinetic model. I hope this is useful. Let me know in the comment section, and I will see you in the next video. Bye bye.